So in physics, one of the things that we do is take things that we can observe, such as motion, something moving around, and we create other representations of it, other models of it. Two really important models that we use for motion are position time graphs and velocity time graphs. In this video, one of our soldier friends is going to help us out with some movement, and then we're going to take that movement and create a position time graph and a velocity time graph of it. We'll also calculate a few things about the motion, which are displacement, distance traveled, and the velocity during each of its intervals of movement. All right, so let's check out the motion. Here, we've got a toy soldier starting at positive 40 centimeters on our number line here. It's going to start moving to the right. Then at 4 seconds, it's going to reach 100 centimeters. It'll stay there for a couple seconds, and it's going to sprint back to the left, reaching a position of 0 centimeters at the end of the 10-second interval. One more time, toy soldier starts at 40 centimeters, moves to the right, reaches a position of 100 centimeters at 4 seconds, stops for 2 seconds, then sprints back to the left to a position of 0 at the end of 10 seconds total. So on the screen, I have a position time graph and a velocity time graph. I'm going to start by creating a position time graph for this motion. Now I know the toy soldier started at a position of 40 centimeters, positive 40 centimeters. So I'm going to make a little dot right there to indicate that starting position when the time was 0 on the stopwatch. As soon as the time started, this toy soldier was moving in the forward direction, or to the right, which I'm defining as the forward direction. And at the end of 4 seconds, it reaches a position of 100 centimeters. Now, the whole time it's moving in that forward direction, it's moving at a relatively constant speed. I'm going to connect those two dots with a line. The fact that it's not curved means it's going to have a constant velocity during that time. If the velocity were changing, let's say the toy soldier was starting slow and then getting faster and faster as time goes on, we'd have a curved line there. But the line's straight because it's a constant speed. Now the toy soldier is going to stay at the position of 100 for a couple seconds. So I'm going to extend this line out, keeping it at the same position of 100 for 1 second and then another second right there when my clock is at 6. As soon as the stopwatch hits 6 seconds, the toy soldier is going to sprint in the opposite direction, and it's going to reach a position of 0 once the time gets to 10 seconds. And again, that's another constant speed that the toy soldier is running at, and so I connect that with a straight line. Now you can kind of see on the graph, I've got really 3 intervals of time. I've got one where the toy soldier is moving forward, one where it's stationary, one where it's moving in the backwards or negative direction. So I'm going to separate those intervals and label them A, B, and C, just so I can talk about the 3 different intervals. Also notice I connected a dotted line down the position graph to line it up with my velocity graph. And that's going to help me whenever I create my velocity graph from this in just a minute. Now in order to create my velocity graph, it'll be helpful if I calculate the velocities in each time interval. So we can do that real quick. The velocity in interval A, well, I need to find the slope. The slope of the position graph is always going to tell you the velocity of the object. That's always going to be the case. So to find the slope here, I'm going to look at the starting point and the ending point on that line. Really, it could be any 2 points on the line, but I'm going to use the starting point there and the ending point up there to calculate my velocity. I'm going to find the slope of it, which is rise over run. The rise here is from 40 to 100. In other words, it traveled 60 centimeters forward in that time interval, so positive 60 centimeters. And how long did it take to travel that far? Well, it went from 0 seconds all the way to 4 seconds. So I would divide by a change in time of 4 seconds, and I get positive 15 meters per second. The velocity in interval B is a little bit easier to calculate because it didn't move. And if something's not moving, that's a speed or a velocity of 0 meters per second. And finally, the velocity for interval C, I'm going to look at this point right here, the beginning of the interval, and this point, the end of the interval, and calculate the slope there. So I travel from a position of 100 centimeters to a position of 0 centimeters. And that's going to be a negative rise because I went from 100 to 0. So I went in the negative direction, or the toy soldier went in the backwards or negative direction. And it took 4 seconds to do so. I can see that here the interval started at 6 seconds and it ended at 10. 10 minus 6 is 4 seconds. And so I get a velocity of negative 25 meters per second in interval C. Now from here, the velocity graph is actually pretty simple. Anytime you have an object that only moves at a constant velocity, and the velocity did change, I guess, between intervals, but during any interval, the velocity of the toy soldier was constant. That makes our velocity time graph pretty straightforward. Let's take a look at interval A to start. I've got a constant velocity of positive 15 meters per second. As soon as the stopwatch started, the toy soldier was moving at a velocity of positive 15 meters per second. So I can graph that down on my velocity time graph here. At a time of 0, the velocity was positive 15 meters per second, so I can plot that point. Now after 1 second has passed, the velocity is still the same. Remember, the velocity is not changing. It's a constant velocity during that interval. So the velocity is still positive 15 meters per second. I can plot that point on my velocity time graph. Well, after 2 seconds have passed, the velocity is still positive 15 meters per second. Boom. And I'm going to keep plotting points until eventually I just get this straight line across. I can connect those dots there, and I get a velocity time graph that's just a straight horizontal line. And think about it. This is a graph of the velocity. Velocity is constant. A constant function in math is just a horizontal line. But something different happens in interval B. Suddenly, the toy soldier isn't moving at all. It's got a velocity of 0 meters per second. And that happens suddenly as soon as it reaches the end of that interval. So on my velocity time graph, I'm going to jump down from that positive 15 meters per second and plot a point at 0 meters per second because the toy soldier isn't moving in interval B. 1 second into interval B, the toy soldier is still not moving. So I still have a velocity of 0. And right there I'm going to have a velocity of 0. So I end up with this horizontal line right on that horizontal axis to show that the toy soldier has a velocity of 0. In other words, it's stationary. Now in interval C, suddenly the toy soldier is moving in the negative direction. This time it's going to be a velocity of negative 25 meters per second, and that starts right away as soon as the interval begins. So I'm going to jump down on my velocity time graph to the negative 25 meters per second, and I'm going to plot a point right there. But again, this is a constant velocity. So at 7 seconds, it still has a velocity of negative 25. So I plot that point right there. And I continue plotting those points, and then I can just draw a horizontal line through those to show the velocity. Now the function looks a little bit strange. It's kind of a piecewise function here. But what's happening there is the toy soldier is moving in the positive direction, so I have a positive velocity, but it's a constant velocity. That's why it's a horizontal line. Then I have a constant velocity of 0 meters per second, so I have a horizontal line at 0. And then I have a horizontal line at negative 25 meters per second to show it moving in the opposite direction, faster though, in this case, 25 meters per second. One more thing that we often do with the velocity time graph is we use a dotted line to connect these intervals that are sort of these abrupt changes like that. So I'll use a dotted line to connect those there. And now I have a velocity graph and a position time graph that describe the motion of the toy soldier. You know, I just realized that in some of my calculations I have meters per second instead of centimeters per second, and I've probably said meters per second a few times, but I'm not going to go back and change it because editing videos takes a while and I already recorded a lot of this. Sorry. But everything I'm doing here is in centimeters and centimeters per second. Now before we go, there's 2 more things we can calculate about the motion using our position time graph. One is the displacement and the other is the distance traveled. Now for displacement, we're always going to look at the final and the initial position to see how much the position changed over that whole time interval. We don't care about the path that the toy soldier took though. The toy soldier could run around like this a bunch of times. All we care about is where it ended and where it began. And that equation for displacement is delta x, that's displacement, equals the final position minus the initial position. I'm using the variable x to represent position. Now the toy soldier's final position was at 0 meters minus its initial position, which was 40 centimeters. So the toy soldier's final position was at 0 centimeters, so equals 0 centimeters, and its initial position was at positive 40 centimeters. So I'm going to take 0 centimeters minus its initial position of 40 centimeters, and I get the displacement is negative 40 centimeters. Now you could have also just done that and said, well, it started at 40, it ended at 0, so it went in the negative direction overall by 40. Finally, we'll calculate the distance traveled. Now the distance traveled, we do care about the path that it takes. We're going to add up how far it traveled during each part of its path. In other words, what's the length of the whole path that the object took. So I'm going to find the distance it traveled during each interval and add them up. So in the first interval, it moved from 40 to 100 centimeters. So that's going to be a change of 60 centimeters. In the second part, it was at 100 and then it ended at 100. So that's going to be a change of 0 centimeters. And finally, in the last part, it started at 100, it ended at 0, so that's going to be a change of 100 centimeters. I add those all up and I get the distance traveled of 160 centimeters. Now the fact that it moved in the negative direction at the end doesn't matter for my distance traveled because I just want to know what was the length of the path that it took, not actually where it ended up at the end. Alright, so that's how you can take some motion, create a position time graph, and then calculate distance, displacement, velocities, and then create a velocity time graph from that. Alright, now that we've done that, try to graph this motion. Sorry, I just needed something for the end of the video and didn't have any better ideas.